So, we are now going to talk about some factorial design, okay, all factor combination. So, if you after this, right. So, let us say that he asked for 3 levels, but we will first look at 3 factors. If there are factors A, B and C and each of them has levels A1, A2, B1, B2, C1, C2, each of them have 2 levels. Then the corresponding experiments, if you are doing all the combinations, then it should be A1, B1, C1, A1, B1, C2, like that, all the combinations you need to have. So, it will be 2 raised to 3. Where does this come from? Levels raised to factors. So, I will have 8 different combinations that I will do. This, as you can imagine, the rate will go up very quickly. For instance, if you are trying to do a simple car design, let us not even worry about crash, simple car testing. 7 variables is nothing. Even 2 levels of those 7 variables, you are expected to do 128 experiments. When I say experiments, after that experiment is done, which means you will do it until failure, the car is not usable. So, no one is going to waste 128 cars to build a robust. So, this is not the ideal way to go ahead. This, how do I write it, is given here. Experiment number 1, A1, B1, C1. Experiment number 2, A1, B1, C2, that is what we have here. So, now get used to this kind of a table, where A1 means level 1 of factor A, level 1 of factor B, level 2 of factor B, like that. So, the full factorial designs are too numerous. Some books might use 1 minus 1 or 0 1 instead of 1 and 2. So, do not get confused for levels 1 and 2 I am saying. So, shortcuts to design, for instance, this is a full factorial is a design of experiment, all the possible combinations. If there are 3 variables, each of the 2 levels, then you need to have 8. So, we saw that, right, like you saw that 3 factors, but 2 of them had 3 levels, 1 of them had 2. So, you had to go for 19, sorry 18, sorry. So, that will be 3 raised to 2 times 2. You remember that resin prepolymer example, there since that prepolymer and the adhesive that we assumed was 3 levels. So, 3, how many factors? 2 factor, resin the prepolymer and the adhesive. So, that is 9 times 2. So, that will be 18 experiments, that is what we got. So, that is a full factorial experiment there. Okay. But there is also other types of full factorial experiments that you might already know in a different sense. We will just briefly discuss that, and then have you come across this face centered cube, body centered cube? In one sense, that is what we are talking about. Okay. Imagine that this is x1 and this is x2 variables. What does it mean? Two levels of x1, that is all you are talking about, 4 experiments. The 4 corners of the, in case this is what 2 raised to 2, 2 factors, 2 levels. If I had 3 levels of x 1, I had 3 levels of x 2. Then what happens? I need to have these combinations also. How many? 9 points. 3 raised to 2. Simple. What do you imagine I am going to do? What is the next acceleration easily? Just 2, let us say 1, 2, this is for x 1. X 2, what about x 3? I am having a stuff like this. That is what is the x 3, the depth is what the x 3 is. So, where will the other points be? It is along the x 3 direction. So, it is just a projection. You got it? So, if it is a cuboid like this, then there are 8 points. Does that tally to what we have discussed? It is 2 levels. How many factors? 2 raised to 3 is okay. Now, if this was 3, something at the center, so it becomes difficult. Now, you have to project that. Okay. So, then it is here, then it will be here, then it will be here, then it will be here, okay. And this side, that side. You might also want to have one in the centers here. So, it will be 3 times 3, sorry, not 3 times 3, 3 raised to 3, that is 27 points, right. So, the way that I have drawn is only 9 plus not even 9 plus 9. So, it is only 18, but then you will get points here, this. So, if you do all that, because here you will have here So, I have added 9 points now. So, that will give you 27. Did you get what I did? I just did this. I just sliced in between and I put points there. So, that will tally up to and there will be a point in this stuff, all put together you will get 27 points. Okay. So, this is one way of looking at things. Then what people suggested is you can in order to get some more information, because if you look at projection wise, you are only replicating the designs. So, in terms of x 1, for instance, in this case, if you are taking the projection of x 1 and x 2, okay, in this particular case that we are talking about, if you are taking a projection of x 1 and x 2, any depth information is lost. Though I have 27 points, my valuable information in the x 1 x 2 plane is only 9, because the remaining all are in x 3. They are not any different in terms of x 1 and x 2, they are the same x 1 x 2 for me. You understand what I am saying? The depth, all the depth information is lost. So is the case here also. If you are taking just x 2, what are the information? Only these 3 are my information. The remaining, they do not change, x 2 does not change in this direction. So, there is only 3 different values of x 2 for me. Instead, what people suggested is, can we push this a little bit away here? How do you want to do that? So, they said, okay, let us do something like this. Instead of keeping this guy there, can I have it here? I might not get any information with respect to this point, but certainly with this point I get more information. You see, for the same 1, 2, 3, 4, 5, 6, 7, 8 and 9 points. Now, I will get 1, 2, 3, 4, 5 information in x 2 instead of 3 information in x 2. You get what I am saying from a projection perspective. Then they said, no, you should not have it like this, you should actually have the circle inside, whichever way it is. You can do it and you can get that. Okay. Then there were something called box designs. Box is the name of the guy who came up with this, Box and Benkham designs. Okay. They also grew famous, but at some point in time people suggested that this is not the way to go. We will have to use statistics as the basis to come up with these designs, and that is how there is something called LHS, Latin hypercube samples. We will discuss them. That came into picture. Okay. Okay. So, with this background, we wanted to see the full factorial experiment that we discussed just now has that background. You understand, right, that cuboid, cube, whatever we looked at. Now, orthogonal array is a fractional factorial experiment. What it says is, you do not have to go and factor in all that information. We will give you some spots. It will not give you the entire information, but you can get most of the information with which you can make a decision. So, what are those points? How are we going to go about it? What are those points is something that we will discuss. I will go back to that cuboid example and then tell you, but how orthogonal array itself is constructed is not the scope for this particular course, but we will discuss how to choose an orthogonal array, how to use it, how to analyze the results based on a design of experiment on orthogonal array. Those are the discussions we will have. So, where do you get the orthogonal arrays? There are some websites which offer orthogonal arrays for as many variables as you want. In the field of computer science, people construct orthogonal arrays for about 1024 variables and even more than that. But this is of not great interest to people like us who are in product design, predominantly mechanical product design. In our case, if you go to about 20 to 30 design variables, that itself is too much. So, why I am telling you that is, orthogonal array required for our purposes are already available. You just need to choose the type of orthogonal array. We will see what do you mean by choose.
So far we have assumed that all the factors have the same number of levels. What if there are...
Oh, no, you can have different, no, that is not true. The one that we discussed, the pre-polymer resin, had different types of.
So how did we get to that formula levels to the power of factors? So if all the factors are different level, what is the level that we choose? What are the factors?
We just discussed that, right. For instance, if all of them were the same, you would just do levels raised to factors. The other example that we had 2 factors, 3 levels. So, you did 3 for that particular thing, you did 3 times 3 raised to 2 and then you multiplied it with the 2 factor stuff. Let us say that in that same example you had 4 factors in which 2 of them had 2 levels and 2 of them had 3 levels. Then you would do 2 raised to 3 raised to 2 divided multiplied by 2 raised to 2. That is straightforward. That comes from the full factorial. This thing that I showed you now, 9 projected on the other side will give you 18. That is what we are looking at. It is just like extrusion. When you are extruding only the points at the corner, on the other end also you will get only points at the corner. So, 4 plus 4 will be 8, but when you have a point at the center, when you are extruding, you will extrude that point also. So, along that it will also have a point at the center. So, that is why you will get an additional 9 points. So, it will be 27, but you can try doing that. One of the variables you can make it 2, that x1, x2, x3 that we did just now. You fix x1 to be 2, x2 to be 3. So, when you project, how much should you get? One factor has 3 levels, one factor has 2 levels. What will you get? Sorry? You will get 9, huh? No man. If you have 2 factors with 3 levels, you will get 9. One factor has 3 levels, one factor has 2 levels. How many points will you get? You can either think pictorially or you can do it not mathematically, numerically also. So, one factor 3. So, 3 raised to 1 is 3 times 2 raised to 1. So, 3 times 2 is 6. So, what will happen is 2 factors in x1, 3 factors in x2. You will sweep it along x1. 3 will go from here to there. 3 plus 3 is 6, that is all. If I had a point in between in x, then you will have, you understand what I am saying, right. So, that is not a big deal. I mean, actually that was the reason that I actually discussed that. What I am trying to tell is, to answer your question, I have 3 factors in this guy. If I have to propagate, then I have only at the next level I will have 3 levels for this x2. So, it is 6. How can I, without drawing this, can I say? Yes, you can say, because it is 3 levels for x2, only one factor times, that is 6. In a similar fashion, if I want to extend this guy, so depending on, if you have 2 variables in, not 2 variables, 2 levels in 3, x3, it is just a projection. So, how many you will have? Now 2 times 2 is 4. So, you should have this is 4 times 3 is 12. So, 6 times 2 will be 12 for you. So, I will have 1 here and then I will have something here. Now, if I made this 3 instead, which means when I am projecting I will also have stuff here in between. So, this guy, this guy, this guy, is that right? In between I will have this guy and this guy. So, Now, instead of that 3 times 3 raised to 2, 2 raised to 1. So, 9 times 2 is 18. So, 6 in between 6, after that 6, 18 points. So, this is how, I mean this is just to give you a pictorial depiction. So, what are these orthogonal arrays? They are fractional factorial experiments. It is not the full factorial, it is only the fractional factorial. For example, this is the way which we usually use. It is called L4. The way in which an orthogonal array is called is Lx. X is the number of experiments. When I say L4, it means 4 experiments are there. But you also need to look for this guy, 2 raised to 3. What it is saying is actually 8 experiments can be reduced to 4 experiments. So, it is a half fractional factorial. Okay. In some cases you can also do 2 raised to 4, which means 16 experiments can be reduced to 4 experiments, which is 1/4. Okay. Instead of 16 experiments you will do 4 experiments. One quick stuff of how you can do that. We are looking at a L8 experiment. This can be represented using a cuboid, let us say. There are 3 axes x1, x2 and x3 which represent the factors primarily. But let us say I do not want to do 8 experiment. Is there a possibility that I can reduce the number of experiments, but still get most of the information? That is the whole idea of orthogonal array. Here we are going to see in a pictorial representation how that can be done. For an L8, all these corner points which are represented by the red dots are nothing but your experimental conditions. For instance, if you would say this point as 0 0 0 and this is 0 1 0 and this guy would be 1 0 0. So, there are different combinations, right. All these would refer to the edges or the corners, the corners, the corner points, not the edges, the corner points of the cuboid. Now, I want to reduce these the 8 red dots into 4 red dots. It should also be logical. So, I cannot just knock off the 4 at the bottom, or I cannot knock off the 4 at the front. If I do that, then I am losing one axis information. I am losing the x axis information if I am taking off all these 4. So, there should be a logic behind which we knock off these. Right now, what I am going to do is the red dots that I am going to retain, I will denote them by putting a black color circle around it. Okay. So, let us say that I start with this guy, I am retaining this. So, since I retain this, anything that is directly connected with it, I am not going to retain. So, I am not going to retain this guy, I need to choose a color so that we know that we will not need it. I will take a green color. So, this will go off, this also will go off. However, this guy will be retained because he is not directly connected to that point. So, interestingly, if you see, if you take only this plane, the plane of x1, x2, this is x2, this is x1, actually there are 4 points to represent the corners. What I am trying to do is I am only taking the 2 diagonally opposite points. We could have started with this point, then we would have ended up retaining this point. So, right now I just started with this point, hence I am retaining this point, the other 2 which are connected to this directly are knocked down. Similarly, on the x3, I will have to knock this out because this is directly connected to it. So, I am going to knock this guy off. Now, we will have to go to the next plane, which is represented by this plane, which is kind of the back end plane. So, this is knocked out already. What I want to do next is, I have 3 points 1, 2 and 3, but as we know this guy is connected to this point. So, I will not have this. So, the only two other remaining guys are naturally these two guys. Okay. So, if you see the 4 points that we have chosen, they are not directly connected to each other. Okay. There is at least one more point that is intermediate, and we are able to get these points. Pictorially, this is the idea behind which the reduction works. Basically, we are trying to go from L8 to L4. What does it mean? 8 experiments to 4 experiments. I have to run half times L8 to go to L4. 8 number of experiments need to be reduced to 4 number of experiments, which obviously means you need to knock down few experiments. The ones that we have marked with the green crosses will indicate those experiments that you want to get rid of, meaning indicate the experimental setups that you want to get rid of. For instance, let us take this case that x1 has 2 levels. Just trying to. So, this is x1, right. So, this guy is x1, he has levels 1 and 2 here, and this is x2 that has levels 1 and 2 here, and this perpendicular to the plane of the monitor is our x3, and that also has 1 and 2 here. What we are trying to see is in the L8 all combinations would have been possible, but right now that might not be the case. This will be reflected when you look at an L4 array compared to an L8 array. So, this is the basic idea by which the rows are knocked down. Accordingly, as a result of it, the columns also will reduce, because if you take 2 level cases, L8 will have how many columns? It will have 7 columns. Similarly, L4 will have 3 columns only. So, the number of factors that can be accounted also goes down. When I say factors, it is not only the main factors, but it also means the interaction factors. It could be 1, 2 factor interactions, or it could be higher order interactions as well.